Hello, in today's video we're going to be talking about section P of our catalog, pilots and relays. If you're interested in other training opportunities, also check out our website at kimray.com/training. There are a lot of products in section P of our catalog with subtle variations, a lot of different models. A couple things to clarify before we dive into it. You'll hear me say low pressure, high pressure, and then there's kind of like the Bellows controlled pilots are actually high pressure. I've mentioned before in these videos that 300 pounds is the line for Kimray products, mostly, and sometimes in our industry, that's the dividing line between high pressure and low pressure, either sub 300 pounds or above 300 pounds. For the pilots and relays, a 300-pound pilot, which we'll look at here in a second, is considered a high-pressure pilot because we also have low-pressure pilots that operate below 20 psi, but then we have the Bellows-controlled pilots that operate, up above 500 pounds. So just a couple distinctions we need to make there. When I'm referring to pilots as an ouncer's pilot, that just means the low pressure pilots. So anything from a few ounces to 20 pounds. If you hear me say HPG or 30 HPG, that's just referring to the diaphragm controlled pilots. If you hear me say PG pilots, I'm referring to the Bellows controlled pilots. Just old language versus what we're referring to them now, just so we're all on the same page. So pilots and relays on their own don't do anything. They need to control something. They are communicating with other pieces of equipment, other control valves, and controlling certain processes. Just like a control valve on its own won't do anything, it needs a pilot to tell it what to do. And so all of these pilots that we'll look at are helping to control processes. Here you can see a couple examples of the pressure packages that we can make with these pilots. We're going to talk about just the pilots today and not the other accessories that make up those packages. We've got tons of content already on those pressure packages, really good animations if you're curious on how those work. The first pilot we're going to look at today is the diaphragm-controlled pilot. I would refer to this as the 30 HPG pilot. So this will work in any application that's below 300 psi. It controls pressure. So it's going to be monitoring either the upstream or downstream pressure of a control valve. It can be used in both back pressure and pressure reducing applications. This is the indirect acting pilot. So when monitored pressure goes above its set point, it is going to be venting the pressure signal going to the control valve. When the monitored pressure falls below the set point, it is then going to have an output to that control valve. And that's true for both standard back pressure and pressure reducing applications. Because back pressure applications, you're wanting to monitor and control and protect what's upstream of the valve. So those valves are going to be fail open valves or pressure to close valves. In a pressure reducing application, you're monitoring, controlling, and protecting what's downstream of the valve. And so that's going to be a fail closed valve or a pressure open valve. Those are one and the same. And so the standard setup for this pilot is indirect acting. Now, if you have an application where you need the opposite of that, you can get these in direct acting versions. We won't really cover the direct acting version of these today, but just know that it is available if you do need that. So here in this diagram, you can see that the orange is the controlled pressure, or that's going to be the monitored pressure. So that's going to be hooked to the downstream side or the upstream side of your control valve, depending on if you're controlling back pressure or you're trying to reduce the pressure. So that pressure is communicated to underneath the spring and the diaphragm assembly on the pilot. As that pressure increases or decreases, it's working against that spring. So the more tension you have on that spring, the more pressure it takes to overcome that tension, and the higher the set point will be. When that monitored pressure does overcome that spring tension, it moves the pilot seats, the upper seat, up or down to adjust the output of the pilot. You supply this pilot with 30 psi of supply pressure. Now you can do that with natural gas or compressed air. Either one will work. When you're using this with our high pressure control valves, the compressed air for supply is completely separated from process flow, so you don't have to worry about that oxygen mixing with processed gases. The teal color is the output of the pilot, so that's the line that's going to the control valve. That 30 psi supply pressure actuates the valve, and then when that valve needs to move again, it vents that signal back through the pilot. You could also capture this if you've got a low pressure gathering system. You just want to make sure that the differentials in that system are high enough where the pilot does not have trouble venting into that line. But you can capture it. It's just a 1/4 inch threaded spot. You could put tubing into that to capture that vented signal. Or if you're using air, you just vent straight to atmosphere. All right, up next is the diaphragm-controlled low-pressure pilots. Its operating range is from 1/2 ounce up to 20 psi. There's 3 different spring ranges, so just make sure you're selecting the correct spring range for your application. The spring is a lot lighter. The surface area of the sensing diaphragm is much larger because we're trying to sense and control much lower pressure, so we need that larger surface area to create enough force to actuate against the spring. If you do have applications that are right around that 10 psi, there's some overlap between the pilots. Be aware of that. If you are around 10 psi and you're never going to be above that, it's probably a good idea to use the low pressure pilots instead of the diaphragm controlled pilots, just because you'll have a wider operating range. You can dial it in a lot better than if you're operating at the minimum of the diaphragm controlled pilot. All right, next up we've got the Bellows controlled high pressure pilots. So the main difference between the diaphragm and the Bellows controlled obviously is the bellows and diaphragm. Diaphragm is limited to 300 psi. I can't go over that, or the diaphragm could rupture. The Bellows design allows you to go much higher pressures. There's 3 options in the Bellows controlled pilots. We have the 75, which is good up to 750 pounds. We've got the 150, which is good up to 1,500 pounds. And then we have the 250, which is good up to 2,500 pounds. Think of the Bellows as a kind of like a metal accordion kind of thing. There's a lot of surface area. Even though the Bellows is relatively small, there's a lot of surface area that pressure can act on and constrict that Bellows. And so it makes it to where you can operate at higher pressures. We used to have a 50, but its operating range was encompassed by the 75 pilot. And so we discontinued that a few years ago. But there might still be some out there. So if you see a 50, it's nothing weird. It's still our product, just not something that we make anymore. Much like the diaphragm-controlled pilot, the Bellows-controlled pilot operates much in the same way. We've got the sensed pressure. that goes around the bellows, and that is constricting that bellows, which in turn is working against the tension on the spring. So the more tension you have, the higher the set point. Less tension means a lower set point. Again, supply pressure is just at 30 psi, and you can use compressed air or natural gas for supply of this pilot. The output, again, goes to the control valve to operate it, to actuate it, and then it is vented back through the pilot. So if you want to capture the vented gas, you can do that at the pilot, or if you're using compressed air, you don't have to worry about that. With the bellows controlled pilots, you can have both gas and liquid on the sensing line. If you are going to be using it in a liquid application, make sure that there is no vibration. With the bellows, you can have liquid on it, but if there is high vibration, you stand the chance of cracking the bellows and the pilot failing. So just make sure that it's not, high vibration, not on a compressor skid if you are using it in a liquid application. Most of the time, people use this for gas control, so back pressure or pressure reducing applications, but you can have liquid on the bellows, and that's not going to affect the way that it operates. All right, next we're going to talk about volume boosters. So this is our relay. It's a volume booster. You would use this in applications where a pilot, can only output 30 psi, but let's say you needed more pressure to actuate larger valves or different kinds of valve that, required higher pressures up to 300 psi. So this relay takes in that variable signal, that up to 30 psi signal, and when that signal gets to the relay, it then boosts that signal up to that higher amount, whatever that is, up to 300 psi. So there's a lot of different connections coming into the relay. The variable pressure comes into the top, and that's more or less your on-off signal. Then you supply the relay with whatever pressure, whatever supply pressure you're wanting to use, what you're wanting it to boost up to, and then it will have an output to that controller or to that valve or whatever you're controlling in that application. It's just a way that you can use existing equipment, existing pilots, but get a higher pressure output from them. We also have the manual reset pilot, which operates a lot like the relays, but it has a manual reset. So anytime that variable pressure is sent to the manual reset pilot, it trips the reset lever and doesn't allow any supply gas through it. You would use this in applications for high temperature or high pressure shutdowns. Commonly, it's used in conjunction with our T12 temperature controller for a high temperature shutdown. We have some videos on that if you want to check that out. But anywhere you're wanting to manually shut down a process and then have to reset it after you fix it, this is where you would use the manual reset pilot. All right, up next we've got the Bistable pilot. Some people say Bistable pilot. I've always said Bistable pilot. I'm not sure what the right way to say it is, but I'm sticking with Bistable pilot. This pilot's used in applications where you're wanting there to be several inputs to the pilot, but one signal needs to take priority. The two variable signals, or the on and off signal, come in on the top of the pilot, and then right underneath that diaphragm is the on signal, the off signal on top. But this pilot will stay in any given position until it receives the opposite signal. Common applications are both liquid and pressure gap control. So you would have two pilots signaling the bistable pilot. you'd have an on signal and an off signal, both going to the bistable pilot. So in a liquid gap control application, you would have a high liquid level controller and a low liquid level controller. If the liquid in the vessel was at the lower liquid level controller, that would be the off signal. So to close the valve, so liquid level has dropped in the vessel, you're wanting to close the valve. That controller sends that signal to the bistable pilot. The bistable pilot will then hold that off signal until the liquid level reaches the higher liquid level controller in the vessel. Once that has an output to the bistable pilot, it then holds that on signal until it drops to the low liquid level controller. So it oscillates between the high and low liquid level. Once it starts going one direction, it'll never start changing to go the other direction until it reaches the other liquid level controller. Same thing with pressure gap control. 2 pressure pilots. You could do this with the ounces valve, with the diaphragm controlled pilot, or the Bellows controlled pilot. But it'll oscillate between 2 set points. So you have a high set point and a low set point, and it'll just oscillate between those two. We also have an electric pilot. This can be used with any electric actuator. It's a way to automate a control valve. It's a way to get away from emissions. It's a green option. But the Kimray electric pilot is really versatile in the applications it can be used in. It can be used in back pressure, pressure reducing, pressure differential. It can be used in gap control. It can be used as a timer. A lot of different applications in one product. But it takes whatever signal you're inputting into it, whatever pressure signal, or if it's a timer, and it outputs a signal to a electric actuator. You can also use this pilot in the package on a electric valve controller, so it kind of mixes pneumatic and electric together. The pilot is monitoring your control pressure, flow, whatever it is, and then having an output to an I to P, which is then converting that 4 to 20 milliamp output into a pneumatic output to the valve itself. So it's kind of a mix between pneumatic and electric. The benefit to that is that you can retrofit valves without having to change them out completely. So if you've got all pneumatic valves and you're wanting to automate that system without having to change over to electric actuators and go all electric, you could then use our pilot to be the in-between from electric to pneumatic. The pressure differential controller is used in applications where you are wanting to control a difference in pressure across a orifice plate. You might hear this referred to as the PDC controller, which is just pressure differential controller, either the 100 PDC or the 200 PDC, and that just has to do with the operating pressure. But the differential that it controls is not that much. That's just the maximum working pressure of this pilot. The controller has inputs for both the upstream and downstream pressure. Those two pressures work against each other with a spring in the pilot. That spring is what controls the difference between those two pressures. The output of this pilot can be both compressed air or natural gas. Again, 30 psi is all that's required. The more tension you have on this spring, the higher the difference between upstream and downstream pressure will be. So when you're metering gas, for example, you're using an orifice plate. If there's a known pressure difference between what's on the upstream side of that orifice plate and the downstream side of that orifice plate, you can calculate the flow rate. And so that's what this pilot is doing. It's maintaining that pressure differential across that orifice plate. Let's say that you're operating at 500 pounds on the upstream side, of the orifice plate. Downstream, you've got 495. So there's a 5-pound differential. If the upstream pressure increases by 5 psi, the downstream pressure is also going to increase by 5 psi. So that way you keep that same differential even though that pressure is changing. If the downstream pressure changes for whatever reason, the pilot will actuate a control valve to also change the upstream pressure. And so no matter what pressure changes you're seeing, this controller will maintain that pressure differential across that orifice plate, which helps you maintain flow rate and keep that consistent. With all of these pilots and relays, we offer repair kits for them. And so you can repair if they do break down, or your elastomers after a certain amount of time start to break down, you can repair. We have videos on most of the pilots, how to repair them. But if you need help repairing, you can always reach out to us and we can help you through that process. Thanks for watching this video. If you've seen our pilots or relays be used in unique applications, or if you have questions, be sure to comment below. You can also check out our other videos in this series of Beyond the Basics.